Orbitals and bonding. Alright, so recall from Gen Chem that there are different types of atomic orbitals where electrons are supposedly in existence or prefer to be. They're pretty much probability areas, so it's most probable to find electrons within that area. So you had s orbitals, where your first electrons would go. The s orbitals is spherical. Then you have the p orbitals, which are dumbbell shaped, and you have d orbitals, which are just really elongated p orbitals. All right. These are all atomic orbitals. You can also have an sp hybridized orbital. Hybridized orbitals where you pretty much have a p orbital and, well, there's the p. You have an s orbital. The s orbital that forms a somewhat weird shaped asymmetrical sp hybridized orbital. Now this is still an atomic orbital. It just happens to be one of the most common ones that we encounter in organic chemistry. We need to mention molecular orbitals, which are pretty much what happens when bonding occurs. So bonding is the overlap of orbitals. So say we have a hydrogen molecule, so just H2, right? Hydrogen has its electrons in an s orbital, and the other hydrogen must also have its electrons in an s orbital, and those orbitals must overlap. Now this would be your two atomic orbitals, but a more correct depiction of that would be a molecular orbital, because that is now the overall average area in which electrons would be found. So as I just said, orbitals need to overlap for bonding to occur. And as we see, two atomic orbitals forming a bond create a molecular orbital. Now, there are two types of overlap that we encounter. We have sigma, Greek letter sigma, bonding, which is just a single bond. In other words, you pretty much have two orbitals overlapping each other, whether it be two s orbitals overlapping, or say an s and a p orbital overlapping, right? Or even maybe a s orbital and an sp orbital, which, recall, is not overlapping, it's just those orbitals exist at the same time. So it's a hybridized system. All right. Now, of course, these two look the same. All right. We then also get pi bonds, as in pi bonding, as in the pi, the same as you know from maths. This is seen in double bonds. So this is when two p orbitals overlap each other sideways. So how does that look like? Something like that. You will notice that there is overlap on both lobes of those orbitals. Now, we use shorthand for sigma bond and pi bond as single bond and double bond, but that's kind of a lie. Usually what it means is that if there's a single bond between two carbons, this is a sigma bond. But if you have a double bond between carbons, let's get a different color. We would say that this is a sigma bond, and the second one is a pi bond, which comes from the sum of two s or p or sp orbitals forming the sigma bond, and then pp overlap to form the pi bond. What about a triple bond? Well, a triple bond would start with a single bond, and then we need to start adding a extra pi bond, and then let's throw in a third pi bond. So in other words, we have 2 pi bonds and 1 sigma bond combined to make a triple bond. Now, of course, this doesn't seem to make that much sense, but that's just how it is. And for shorthand, if you ever get asked where are the pi bonds, just know that you point towards the double or triple bonds present. If there are no double or triple bonds, then you can say that there are no pi bonds in a molecule. Okay? Alright, let's move on to the important stuff. We need to focus on hybridization. So this is pretty much the terminology you need to learn. You have sp3 systems where the atom, in this case carbon, only has single bonds. So in other words, you have a carbon that is tetrahedral. So we would say that all of these carbons in this system are sp3. Okay. If you need to look it up, read the textbook and go over your Gen Chem notes if it doesn't make sense. If not, come to office hours. But pretty much what you need to know is that if there are only single bonds in a carbon, we refer to it as sp3. It is also tetrahedral. So sp3 carbon is tetrahedral. Alright, we then have sp2. This is when the atom, once again we're going to focus on carbon, has a double bond. Okay, this is, for example, in this case. These 2 carbons here are sp2, and this one here is still our friendly sp3. Notice that this is tetrahedral because it is sp3, whilst these sp2 carbons are trigonal planar. Just like Vesper theory says, you have 3 electron domains around the carbon, therefore it's trigonal planar. The sp hybridization also tells you this. Now, why is it sp3 instead of sp2? We could say that sp2 has 1 less p orbital hybridized. So what it also means is that when you have this double bond, the p orbitals overlap, making this whole system become planar, i.e. in the trigonal planar. So now we know how orbitals cause the shapes to shift in the way they are. Finally, we get to the sp orbitals, which is the atom, in this case carbon, with a triple bond. Right? And sp carbons are always linear. Now, just like sp3 had one more p orbital hybridized versus sp2, it means that there are two p orbitals that are not hybridized in sp. So when you have your carbons, you end up having two p orbitals pretty much orthogonal to each other, right? And then you just end up with one hydrogen sp sticking out. So these form a double bond, well, a bond, I guess, and these form a bond. So let's color them in just to emphasize that. So we have green, 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 and we have the red and the red. You'll notice that they are orthogonal to each other and overlapping, giving us the triple bond. So if we count them, we still have one sigma bond in the middle. We have the green pi bond. We have the red pi bond. But because of the way these orbitals overlap, it causes the hydrogen to stick out parallel with the carbon-carbon bond, making it linear. And that is all I have for you at this point in time with respect to hybridization.